Hello, my name is Sahil Dua, and I'm going to talk about long, short-term memory, LSTMs, and so it's going to be a talk about LSTMs, but it's not just going to be focused on LSTM, it's going to be how and why we need LSTM and how we can implement that using TensorFlow. So before we start, a quick introduction. No? Okay. Yeah, so I'm a developer, not a machine learning data scientist. I'm a software developer at Booking.com. I've been working with machine learning models a lot, but that's not by my title. And I'm an open source community leader at DuckDuckGo. And besides that, I'm a contributor at a bunch of projects like Git, version control system that probably most of you have used at some point. Projects like Pandas library have a couple of patches to the library, Go GitHub project by Google, Linguist, which is a project by GitHub to identify the language of any file that you commit to the GitHub, and a bunch of other projects. So before we start, let me go through the brief agenda of how this talk is going to look like. And so first of all, I'm going to talk about deep learning, why deep learning is useful in the field of natural language processing. Then I will be talking about the word representations, how to represent the words and why that representation is important, why do we care about that. After that, we'll see, once we have the representations, how do we handle the sequences of words that we have? And that's when the LSTMs will come into picture, and we will see what are the other alternatives we have and why LSTMs are important, what problem they solve. And after that, it's a practical part where we'll be implementing LSTM using TensorFlow. So, let's begin. First of all, a quick quiz. Who all has experience of working in natural language processing? Okay, cool. So just to brief, natural language processing is the process of making computers, making machines understand or process language to do some task. Basically, given some text, given some language, trying to understand what that could mean and trying to do some task on the basis of that understanding. So some of the tasks related to natural language processing that we have are like question answering. Like you have your bots, Alexa, Cortana, or Google Assistants. All these take your question and try to answer based on something or try to do some action based on the text that you send. Another one is sentiment analysis, which means trying to predict the emotional tone of the text that you have. And another one is image to text mapping. For example, if you have some image, you want to come up with caption for that image, it comes into picture. And if you have machine translation, which is one of the biggest applications in the current time, translating one piece of text from one language to another, for example, from English to German or German to English, or any other language for that case. And another one is speech recognition, which means you have some spoken words, you want to identify what's there and change that into text format. And it's not just an exhaustive list of tasks related to NLP, because you can also combine some of the tasks from there. For example, you can have speech recognition combined with question answering. That's what you have with your OK Google tool that you have. You say something, it identifies what you are saying and understands that, and based on that, it does some action that comes under the part of question answering. So natural language processing has been there for quite a while now. Why is deep learning important? Why is deep learning suddenly helping the problems in natural language processing? So in pre-deep learning era, we have had a lot of success with the natural language processing tasks, and most of the time was spent in the feature engineering, which means you're trying to come up with some features. You're trying to work on the low-level features, like in case of images, you're trying to detect the edges, detect the objects, and then trying to get to the higher level. But with the deep learning, there is no need to do such kind of feature engineering, because you can allow the machines to learn these low-level features on their own based on a lot of data. So deep learning has lowered the barrier for entry into natural language processing, and that's why a lot of research, a lot of deep learning research has been focused on natural language processing tasks, and we have seen tremendous amount of improvements in all the kind of applications that we have. So we know that deep learning is useful for natural language processing, but first of all, let's try to see what kind of other models that we have and what kind of inputs we send to those models. For example, we have convolutional neural networks which work with images, and they take arrays of pixels, basically arrays of finite values, scalar values, and then we have logistic regression mostly for classification. Again, they take scalar values, quantifiable, measurable values, and we have reinforcement learning, which has, again, the reward signals, which are, again, quantifiable and decides which ones, which kind of actions are going to be rewarded based on the reinforcement. But when we talk about natural language processing, we have a problem here, because the pipeline that we have looks like this. We have a text. We have a sentence. The movie was neither funny nor excited, and blah, blah, blah. There are a bunch of words, and what you want to do ultimately is that you want to pass those words into a sentiment analysis system, which is a black box right now, and you don't really have any idea what's going on inside that. And you want to see what's the sentiment behind this text. Now, we have no way to apply our tools like backpropagation or dot product on the strings. So we need to change this string format input into some scalar measurable values so that we can actually do all those stuff that we used to do with other machine learning models or we do with other deep learning models. So this is what we do. This is the desired version that we have. So what we do is we change every word, we replace every word by the vector representation of that word. So for example, in this case, what we do is we have 16 words in that sentence, and we replace every word with a d-dimensional vector, which means now our input is a two-dimensional matrix of 16 into d dimensions. And so now it's just a 2D matrix of scalar values, and you can do whatever stuff you want. You can do dot product, backpropagation, gradients, and all the stuff that you were doing with other machine learning or deep learning models. And these vector representations of the words are known as word embeddings, which means basically you abstract out the meaning of a word in terms of the vector, which you can decide how many dimensions you want based on what kind of application you have and how much computation you can afford to have with your model. And these word embeddings now should be in such a way that these word embeddings are sort of abstracting out the meaning or the semantics or the context of the word. For example, if we have these words, we want that the final vector representations of our words, for example, for love and adore, should be closer to each other as compared to love and baseball, because love and adore are going to be more likely to occur in the same context or in the same semantics. So this is what we do. We take the corpus that we have, we take the entire vocabulary of all the words that we have, we assign them, this is the process of generating the embeddings is known as word-to-vec. It's a really famous procedure of changing the words into their vector representations based on the context. And what we do is we take all the words that we have, generate the embeddings, and we decide how many dimensions we want. Like in this case, let's say we have d dimensions for each vector, and we get the embeddings, mapping of embeddings for each word, which we can then go ahead and replace at a later time when we want to process any text. Yep. Yep. Mm-hmm. Yes, so now that we know how to get the word vectors, how to get the vector representations of all the words that we have in our vocabulary, the next is how do we actually handle the sequence of words? How do we handle the sequence of these vectors, word representations that we have, and try to get a sentiment out of it, which is going to be a 1 or 0 value based on if it's positive or negative. So there are a few challenges in dealing with these kind of applications, because whenever we talk about sequences, it always has some temporal effect in that, which means that any word depends on what word comes before it and what comes after it. So we have a bunch of challenges, like one of them is how do we preserve the order of words? Let's take an example. We have a sentence which says the food was good, not bad at all. Another one is the food was bad, not good at all. So these have totally different meaning, but the words are all exactly the same. So we need to preserve the order when we are processing, so that we actually extract the real meaning out of this sentence. Another challenge that we have is how do we deal with the different word orders. For example, we have on Monday it was raining, and it was raining on Monday. So we need to be able to make sure that we extract the same meaning out of these two different order words which have the same meaning. And another one is how do we keep track of long-term dependencies? And this is one of the things that is going to actually lead us to LSTMs. So this is an example. In Berlin, I had a great time, and I learned some of the blank language. We can look at it and we can guess what language is going to be more probable, but for the machine, for the computer to be able to learn it, it has to remember what was there in the sentence at the beginning, and so it has to maintain some sort of long-term memory so that it can still keep that context, and when it knows that, okay, a blank is going to be a language, then it remembers the context and links that to a German language based on whatever we had in the sentence. Another one is how do we deal with variable length of sequences, and this is one of the problems when we tackle when we work with the LSTMs a lot. So we have a lot of sentences like awesome, we have food was good, I didn't like that place at all. All of these words, or most of the words in English, are going to be of variable length. So we can't really build a model which takes a fixed length and process all the words. We have to do some sort of padding, we have to do some sort of truncation to make sure that all the words, all the sentences are of same length, so that we can easily process them as a whole. So you may think that why don't we use feed-forward neural networks for such a problem? Which, for example, we have some neural networks which have some input units, then some hidden units, and some output units based on what kind of output you want. So let's take an example which is not related to linguistics, not related to natural language processing at all. It's related to detecting the activity that's going on in a video. So you're looking at the images in the video, and again, since this is a sequence of images, it again has a temporal effect, and we will see what kind of different models that we have, and we'll see how they behave on this data, and we'll see why we need LSTMs to solve some problems. So let's see. First of all, let's forget about the sequence at all. Let's forget about the sequential nature of the movie that we have, and let's focus on one image at a time. So what we do is we build a neural network. We pass one image at a time, and it's going to give us a prediction based on that one image only. So what it's going to do is it's going to learn, probably it's going to start with learning some low-level patterns like detecting edges, detecting some objects, and some curves in the image. And as we feed more data, it's going to learn about some high-level features like face or body or some animal or some objects at a high level. And if we feed even more data, it's going to be able to learn what kind of activity is going on. For example, if we see that in an image we have some humans, we have some folks, steaks, it's going to be likely that people are eating. Probably people are eating in that image. So this is what neural network will do. Let's take this example. So we have an image in which a Snorlax Pokemon is getting hit by water. What neural network is going to see is it's going to see that there's a Snorlax, there is water, he's probably taking a bath. So the probability of captioning it as Snorlax is showering is going to be highest, and Snorlax is being attacked is not going to be even considered at all. So this is what happens when we don't consider the sequential nature and we just focus on one particular image. Before we move on to other alternatives to improve the behavior, let me talk through the neural network, how it works mathematically. So it's simple that we pass the input. We have some neural network, which means like we have some hidden layers, some architecture which takes the input and gives the output based on what kind of output, how many units we want. And how it works is that, let's say X is our input. We have some W matrix, which is the weight matrix connecting the input units to the hidden units, and you get some sort of sigmoid or any activation function, and that gives you the activations for your hidden layer, which is H. And so on, you go and you take the output by having another weight matrix which connects V, which is V, and which connects your hidden units to the output units, and you get your output as a probability of that photo being anything between the options that we have, if it's classification or if it's regression based on that. So this is not cool. We saw that. So how about remembering some information about the scenes from previous scenes so that we can use that information to make a prediction better than what we were doing with the neural networks when we were looking at just one picture. Because not considering the sequential nature of images or of words is really machine learning 101, and if you don't really want to go into sequences if you're not going to consider how they are changing based on their memory. So recurrent neural networks, and what they do is they use the previous information, previous knowledge that they build whenever they are going to predict something. And another thing they do is then they store the knowledge that they gain from the current prediction. For example, if we pass some images related to that, some person is on the beach, it's more likely that any image after that, if that image is of a person lying on a ground with eyes closed, is probably sun tanning instead of that person sleeping or that person being dead. So this is the kind of problems when we are trying to remember the information that it has seen already and trying to predict on the basis of that. So let's see that example again. This time we have two images because you decided to consider the sequence. In first one, we see RNN is going to see, okay, it has some initial memory which says battle scene has started. Then it's going to see, okay, there is a battle and I see water coming out of a Pokemon. So it's probably attacking, and it's going to detect this as Pokemon is attacking. So it does two things. One is it sends some prediction based on what it has already learned. And it's going to update its memory as well so that it can use that for further predictions. So it's going to save in the memory now that it's in battle, enemy is water Pokemon, and enemy has launched attack. So that whenever a next image comes, it remembers that context that enemy was attacking with water. It's going to remember that. And as we see that in the next image, it's going to say, okay, I remember we are still in a battle and Pokemon was attacking, so Snorlax is probably being hit. And that's what is actually happening, and it's able to detect the correct answer, which is Snorlax is being attacked based on the previous memory that it learned from the previous predictions. And again, it's going to do the same thing. It's going to store some of the information that it learned from this current prediction, and going to store that into its memory for further predictions. So how does this look like? Again, we have some input. We send that to the recurrent neural network. And the only difference that we have is that instead of just predicting one value at a time and not considering anything that happened before that, it has a working memory. It's a memory state that helps it to retain some of the knowledge, some of the information that was there in the past, and try to use that in all the subsequent predictions. And mathematically, it's still the same, except one part, that we had only W metrics for combining the input units and hidden units, but now we have another one, which is U, which decides how much of the previous memory. So HT minus 1 is the output, or the memory that it built on the basis of previous state. So how much of that memory is going to be used at this time? It decides that and gives the output again. So while this looks really good, there are still some problems with RNNs. So we are able to look at the current changes and able to store some changes, store some knowledge about the state. But there are some problems, like it's not really able to keep the long-term memory because of the nature of how it's implemented. So in the back propagation, what we have is we have a product of a lot of gradients. And if we consider the gradients being small at some point, it's going to be diminishing in such a way that it's almost going to be zero, and it's not going to consider any of the values from far away from the current point. So it's not really maintaining the long-term memory. It's maintaining some sort of memory from the previous value because it's not really controlling the way it's updating its memory. And another one is the memory update is really chaotic, which means, for example, if we pass one image which is of some landmark in US, let's say America, and it's going to learn that, okay, we are in America, the scene is in America, but if the next moment we pass it something in for example, in Germany, it's going to forget about it's going to completely forget about that we were in US. It's going to only consider the Germany part. So what it means is that the memory update is very chaotic. It's getting updated very frequently. So it's not easy to retain the information for a long time. Whenever we see something different, it's just going to wipe it out and replace that with a new memory. So that's the problem that we have, and this doesn't really help us in having the long-term memory so that we can detect the sequences, we can work with the sequences in a better way. So, long and more controlled memories with LSTMs. So, how this works is, it has three mechanisms. The first one is forgetting mechanism. If the LSTM model sees something, it decides whether the previous information is still useful or not. So basically there is a mechanism, there is a way to control how much of the previous information is going to be forgotten and how much is going to be retained. And another one is the saving mechanism. If it sees something new in the current prediction, it's going to decide how much of that new information is going to be stored and how much of that is going to be ignored. And the third one is using mechanism, which means how much of the memory that it has is going to be used in making the current prediction. Let's go through them again. So we have some prediction, we have some long-term memory with the LSTM. It's going to first of all decide what parts of the current state are not used at all. So it's going to forget some of them and going to retain some. Then it's going to decide what all new information is going to be useful for future predictions, and it's going to store only that information and going to get rid of any information, any new information that it thinks it's not needed. Another one is output. So what information of the memory that we have is going to be used right now? For example, if we see that some person, Bob, is not in the scene at the moment, we don't want to erase all the information about Bob, but we want to make sure that we are able to get more information about other things, and we are going to retain the information that we have about that character. And similarly, if we have some character in the scene, we want that we are able to collect more information without actually forgetting the other information that we don't have. So let's look at the same example again. This time we have some long-term memory which says Snorlax likes bamboo. 1 minute into battle, enemy in the center of the screen. So this is a bunch of information that it has. And some working memory, which means 1 minute into memory, into battle, and enemy in center of screen. So this is what LSTM is going to do. It's going to see what should I forget. It's going to say, okay, Pokemon's location is not important, so it's going to forget that. It's going to see what should I save new from this particular image. It's going to see that it should save the state of the Pokemon in this case. And then it's going to see what should I ignore. And it's going to ignore some of the things from the memory that it had already. And based on that, it's going to give the output as well as update the memory. And the updated memory is going to be based on what decisions it made on all of these 3 stages. And this is how it looks like. So we had RNN, and we had only 1 memory state. But with LSTM, we have 2 memory states. One is the working memory, which means the memory that it's going to use in the current prediction. And there is a long-term memory, which is going to be stored so that we can use that in subsequent request. For example, in that case of in Berlin, I had a great time and I learned some of the blank language. So it's going to retain the information about being in Berlin and going to use that context to detect what language it could be, what word can go in that blank. So there are some mathematical equations, which means, so we have 3 mechanisms in this. One is remembering, one is saving, another one is focusing what parts to focus on. All these 3 parts are actually small neural networks. Actually small RNNs, recurrent neural networks, which means it decides on the basis of what's going to remember. It multiplies that with the previous state that it has. Then it decides what to save, and everything that's not saved is going to be ignored from the current state that we have. And then it sees what information do I need to focus on at the moment so that I can make the prediction, and that's what it uses for sending the prediction. And all these remember, save, and focus are the same, have the same expression as we saw with the recurrent neural networks. So with all these maths, this was all about the theory. Now the next part is going to be about implementing LSTM with TensorFlow. So I'm going to work on a Jupyter notebook, and let me just get some of the things off. Yep. So first of all, how many of you have experience of working with TensorFlow already? Okay, quite a lot. So we're going to start with some of the basics, and I'm going to skip if you think it's going to be redundant. So first of all, we go with including all the TensorFlow libraries, or TensorFlow library and other required libraries that we want. And then we're going to build a very basic graph, computation graph. So how things work in TensorFlow are that we have some computation graph, and we build that computation graph before actually doing any computation. And based on that graph, then we run a session in which we execute that graph, and TensorFlow takes the input values into that graph and does operations that we had defined while building the graph and gives the output. So let's build this graph where we have 2 inputs, A and B. We want to find A plus B into B minus 1. So what we do is, we have A, we build the placeholders, which mean these are the placeholders for the values that are going to come in future. So whenever we want to run this computation graph, we are going to pass these values. And before that, we can just specify that it's going to look something like this, because we say, okay, float values, and we don't really tell what size it's going to be or what value it's going to be. So we define the operations. C is equal to TF add, which is an implicit function for adding 2 values. Then we have D equal to B minus 1, and we do the E multiply of C and D. So at this point, we have only built the computation graph. We have built all the all the operations that we wanted to do. And the next step is to create a session and run this graph with some values so that we can get the output. So what we do here is we have two values. We say, okay, A is going to be 3, B is going to be 6, and we pass that as a dictionary. So how it works is that it has a dictionary with all the placeholder values, and if you don't pass any of the placeholder values, it's going to complain because it doesn't know what value to put for that placeholder. So what we do is we simply session.run with what operation we want to compute. In this case, we want to compute E, and then we pass the feed dictionary with all the data that we had. And if we run this, it's going to give us output 45 based on what values. If we change the values, it's going to give different results based on the values that we pass. So it gives us a flexibility to be able to pass any input, just build the graph and pass any kind of input that you have, and not worry about having to implicitly build the constants into the graph. So now let's talk about LSTM. So the application that we are going to build today is going to be sentiment analysis. So basically we have some tweets, and we are going to build LSTM to learn the sentiment behind those tweets, and we're going to train the model using TensorFlow. So first of all, this is what it's going to look like. This is what our model is going to look like. We're going to have 2 LSTM layers, and when we talk about layers, it's simply the same kind of layers that we have with neural networks, which mean we have one layer, and output of that layer goes into another layer, and then that chain goes on. And at the end of the output of the last layer that we have, it's going to be a fully connected layer, which is basically a linear classification that you have, like you have bunch of values, bunch of units, and you have a sigmoid or any kind of classification which gives you 0 or 1 value based on if you have only binary classification. And this is how our data pipeline is going to look like. So we are going to take the input sequence, and as we saw that we can't really do our mathematical operations on the sequence, so we're going to change that into different words, and then the words are going to represent some integers based on some word ID, and then we are going to build embeddings for all those words and going to replace that every word in the sequence with their corresponding vector. So in the end, you can see that it's a vector of dimensions 10 cross 50 cross 1 in this case. So it's basically 10 is the number of words, 50 is the size of the sequence vector, the vector that we have, and then 1 is just a dimension because in this case we don't have any third dimension based on that. So let's start and set up the model parameters. Our tweet size is going to be maximum 20. So as I talked in the beginning, that the sentences that we have are of variable length. So we need to decide what length are we going to consider. Either we are going to need to pad the sentences that we have, or we are going to have to truncate the sentences that we have. So we decide that it's going to be of 20. We see, okay, let's start with the hidden units in the LSTM cell as 100, and this is going to be one of the hyperparameters that you can tune later to actually see what suits your application better. And then we have vocabulary size. This is the total number of words that we are going to have. And the batch size is how many of these words we are going to process in one iteration of the training. Next, what we do is we reset the graph so that all the operations are placed in the right graph, and then we initialize the session. So this is how it looks like. As I mentioned earlier, that so first of all, is everything visible on the backside as well? Okay, cool. So As I mentioned, placeholders are used to build sort of a literal placeholder for the data that's going to come in future, that's going to come. And what we want to do is we want to be able to build a generic graph, computation graph with the TensorFlow, with all the operations that we want, and be able to just pass any kind of data later and run the trainings faster instead of building the graph every time we have new data. So our input is going to look like this. We have a bunch of tweets in this, so that corresponds to the batch size, and then we have a maximum sequence length, which in our case is 20, and then we have word IDs, a sequence, and then this sequence is also going to be replaced by the word embedding. So basically, it's going to be a 3D batch size into maximum sequence length into the word vector length. And then we have some labels which are going to be one-dimensional, which are going to be either 0 or 1, and it's going to be for every tweet that we have, basically. So the size is going to be batch size into 1. So we define these placeholders like this, and if we have this kind of size, we define the size itself. And in this case, we don't you can see the first dimension is not defined. So the reason behind that is we want to be able to build this graph in a generic way that we can iterate with different kind of batch sizes. So that's why we pass that as none. That means it can be variable. So we have none, which is going to be correspond to the batch size when we define it. And then we have tweet size, which is the maximum size. Then we have the vocabulary size. And yeah, so the labels are going to be of only one-dimensional as batch size. So we can see that the sizes are as we wanted it to be. The first size is not defined, and it's going to be variable based on what kind of values, what kind of inputs we pass to these placeholders. So the next step is to build the LSTM layers now. And TensorFlow makes it really easy to build these cells so that you don't really have to do all the mathematics that you saw on the previous slides, that you don't really have to define those three remember, save, and focus neural networks. It gives you this flexibility of just like an abstraction layer of adding the LSTM cells. So what you do is you define one LSTM cell, and then you give it some size based on the hidden size that we decided as 100, and you build two LSTM cells because we saw that it's going to be a two-layer LSTM architecture. So the next step is now to combine these two cells so that we have one multiple LSTM layers that is able to, that has two layers and that is able to connect with each other. So what we do is we have this function for RNN cell. We pass both the cells that we have, and it gives us an architecture of two combined LSTM layers. And the next thing we need to do is now define an operation which is going to actually take the data that we have and going to pass that to the architecture that we build. So we have dynamic RNN, which builds the graph dynamically, which builds this entire architecture dynamically and passes the data that we have. And data in this case is going to be the placeholders that we defined at the previous step. So it's going to be the tweets as we defined, and it's going to be three-dimensional matrix or vector. And as we saw that the final stage of RNN is taking the outputs of the last layer of LSTM and passing that to a linear classification layer, which is basically just taking the inputs, which in this case is the output of the last layer, multiplying that with some weight metrics and some bias, and giving the output as a probability. So we define this generic method which takes the input and gives the output on the basis of that logic. And next we are going to pass the final state. You can see that it's the last layer of the last LSTM cell. So what we do is we take that and pass that to the linear function. Basically, we are going to now classify the output of the last layer, and it's going to give us one-dimensional vector, which is actually the output that we want. So if we run, it's going to give us output something like this. The shape of sentiment variable is one-dimensional, but it doesn't show the size because it's the batch size. So because we have one prediction per object per tweet in the batch, so it doesn't know what size it's going to be, but it's going to be same as the batch size and just one value for every tweet. So the next step is to define the loss. Yeah. So the next step is to define the loss. So now we have two things. We have the actual labels that we have in our labeled data, and we have some prediction values which come from the output of linear classification layer that we have. Now we want to find the loss that we have so that we can pass this loss, pass this prediction error to the model in the backpropagation so that it can actually learn to tune the parameters that it has. So what we do is we use the neural networks library method, which is sigmoid cross entropy with logits. And in this case, it takes two parameters. Logit is the output that you get from the linear layer, and then the actual labels that you wanted. And we find the mean, overall mean loss of all the values in that batch. And next what we do is we have the loss, and what we want to do is we want to see what's the prediction error so that we can try to also keep an eye on that, because if we want to see if our model is actually improving with training or not. So how we do that is we define, so we first of all, we do the activation on the top of the output that we got from linear classification, because it's not directly the probability, it's activation. So we need to activate that, and in this case, we use sigmoid because of the classification, the binary classification. And next what we do is we have some probability for each tweet, and we want to see, okay, if it's 0 or 1. So we define the threshold 0.5, and anything beyond 0.5 is going to be considered as 1, and less than that is going to be considered as 0. And next what we do is we see how many values in that batch are not equal between what we predict and what labels we have, the true labels that we have with that data. And based on that, we find the prediction error, summing all the wrong values that we got. So this is about the different metrics, different operations that we wanted. And another one, now finally to come up with the optimizer, the actual training operation, because this is operation that we are going to be running all the time. And we use ADAM optimization, adaptive with momentum optimization. And it will try to minimize the loss, because we pass that we want to minimize some particular operation. So what it's going to do is it's going to run the forward passes of the LSTM architecture. It's going to see what's the value of the loss, and then it's going to consider the gradients on the basis of that loss and try to backpropagate and try to update the values based on those gradients and try to optimize for this loss variable. And so how we define the loss is really important according to our specific applications. And in this case, it's a binary classification, so we are good with using the cross entropy with logits, and it can be different if you want to do something different, some different kind of output that you want. And this is something that I didn't really mention earlier. So there are generally two ways to represent a word as a vector. One is building the word embeddings based on context, based on the meaning of words. Another one is the really naive way, which means you just take the size of your entire dictionary and you have all zeros in that, and only one value is going to be 1, which is the index of your word. For example, if you have some word which is index 41, and you have size of your vocabulary as 7,000, you are going to have a 7,000 long vector, one-dimensional vector, with all zeros except one value of 1 at 41 index. So basically, you're just defining the words as unique vector as on your scale of entire vocabulary. So that's what it actually does, this method. And I think I forgot to run it, so yes. So it builds the optimizer. Then we have this one-hot encoding, which is going to create the word vectors for all the words that we have in the tweets. And the final step is to run our session. And in this stage, what we want to do is, so we have built the entire graph that we had. And what we want to do now is read the data that we have, make it in a way that our graph expects, and pass it to the graph, and then say what operation we want to run. So let's see how we do that. So we have this data as a sequence of words, sequence of word IDs. And what we do is we read that as a list, and we replace all the tweets with their one hot encoding, which means we change all the word vectors, all the words into their corresponding vectors. And a bunch of different stuff here, and this is where it main step starts. So we have number of steps that are going to be there. So number of steps is equal to how many times we are going to iterate on our, how many times we are going to run our training. And it depends how many times you want. You can actually fine tune that as well based on what kind of findings you have based on your running. And another thing to note is that every time we run the training operation, we are going to take only a subset, only a batch of the tweets that we have. In this case, it's going to be 64. So we're going to take 64 tweets at a time, and going to learn something out of that, and going to take the next batch and do the gradient descent based on that. So what it does is it builds the data, because there were only two placeholders that we had. One was the tweets, another one was labels. And we built that feed dictionary that we passed in that previous simple case. And next what we do is we run the session. And we need to define what operation we want to run. And in this case, we want to run the optimizer, because that's our actual trainer. That's our actual optimizer that is minimizing the loss. We want to run that. Another thing we want to run is loss, because we want to see at every step what is the loss now and what is the prediction error now, so that we can be able to track if something is not going wrong. And then we pass the feed dictionary, the data that we have. And this is going to run that one training step, and we are going to iterate on top of that. And another thing is, this is an optional thing, and what we have here is every 20th step, we're trying to evaluate on our test data. And this 20 is not really a rule. It's up to you how frequently you want to do it. And sometimes when you actually do it in production, it's mostly like you train your model on all your data. You have multiple epochs, and then what you do is you run your evaluation either at the end or at a large epoch number, like after a lot of epochs. And by the way, epoch is the one iteration over your entire data set. For example, if you have 1 million tweets, and you're going to iterate on, let's say, only 200 tweets in one batch, it's going to take a lot of, I think, 50,000 or 5,000 or 500 different iterations to actually iterate over all your data set. And that's going to be one epoch, and you can have multiple epochs, and you can train for a long time so that your model actually gives the good accuracy or whatever metric you have for evaluating the model. So let's run it and see. It takes some time. Whenever we load the data, it's going to build that computation graph that we defined, and then going to read the data and pass that data to the computation graph. And after that, it's going to, so it has started training the data. It has already had the first step, and it computed that the loss was this, and the training error was this. And then it says some different error on the test set, and we will see that as we proceed with this training, it's going to have lesser and lesser test error, and at some point it may have more because of the nature of mini batch gradient descent, but overall it's going to be moving towards better accuracy or lower error on the test set. Any questions? Yep.
You use some of the new utility functions in the network. Could you show how you define the loop unrolling? As you said, the problem with text like this is we have variable length. And one way to solve this is we say we
Yep.
and the rest. And I think at the beginning somewhere you defined your maximum length for a tweet.
Right.
And which of the utility functions, where does he perform the cropping and the padding? So he knows how to unroll the LSTM cells.
Okay, in this case, I think the data that we had was, let me see. Yeah, so we have defined our tweet size, and we have defined that in the placeholder accordingly. And in this case, the input that we have is already of truncated or padded to that list, but if you don't have that, and of course that's going to require some data pre-processing, and what you do in that step is either so if your length of the tweet or the sentence is less than the length that you're going with, you add either zeros or ones or something like that, or -1, which is not going to be there in your actual words, so that the model learns that these values are redundant and there's no importance behind that. And otherwise you truncate and basis off that. Yep.
That's clear, that's the pre-processing, but
right.
He needs to unroll the cells. I mean, the cells need to be concatenated 20 times so you can produce the sequence. And I'm just wondering, because you build the LSTM cells, and then how does he know he has to do that 20 times? Does it recognize that from the input tensor side? Or so which of the functions does unroll it?
Right. Yeah, right. So let me go back to the slides that I had. So I think I showed that in RNN.
Yeah, sure. I know how it works mathematically. I mean,
yeah.
What Python method does.
Yeah, so how it actually does is that it knows from the size of the input, and it doesn't really physically roll the cells, and how it works is that it's going to have one cell, and it's actually going to pass for one word, and then the next word, and another one. It's not physically rolling out the cells. It's basically just one cell, and it's just repeating itself based on that sequence and learning.
That's one of these intermediate functions. That's what I was wondering.
Yeah, it's in this one, in the LSTM cell that we have. When we pass the data from here to our layer of 2 LSTM cells, yeah, it's going to, yeah, right. It's going to make that and flow all the different words that we have through those cells, and it's going to learn on the basis of that one sequence. Yeah.
Is there a way to have some kind of dynamic output? I mean, in my opinion, or what I have understood, LSTMs is kind of many-to-many mapping. So instead of one-to-one or one-to-many with other architectures, and you have defined your tweet with size 20, and then you have one output. Is there a way to extend it word by word and have something like a kind of graph and now I think it's more negative sentence, but then there are 2 or 3 words which make it way more positive. Is there a way to get after each step an output?
I'm not sure if there is an implicit way using the TensorFlow modules, but you can definitely build that using your custom cells so that you can. So basically what you want to do is you want to have variable lengths and want to have the output at every step, right?
So that would be some kind of visualization, which words were the trigger words that the net thinks it's a positive or negative word.
No, I'm not sure about that. Haven't really tried yet. Yeah, no.
I have a question. I've seen also one-dimensional convolutional neural networks being used for sentiment analysis on top of word embeddings. So you said that the very important part with the long-term LSTMs is the memory, the long-term memory.
Yeah.
Have you any experience if you use hierarchy or deep stacking of 1D convolutional nets that also could achieve something similar?
No, I haven't really used convolutional networks for this purpose. No. But have you used and got some results?
So one paper back then, but I have not really had any practical experience.
Okay, yeah, I will check it out. I haven't really used that.
It seems to me these 1D conv nets, they've developed. In this paper, they mentioned at least that they get state-of-the-art
Okay.
performance on some data sets out there. So, but it's
Okay. Okay. Yeah, I'll check that. Haven't really seen that. Thank you. Yeah.
One question. You're using one-hot-coded data that's binary coded.
Mm-hmm.
Do you know whether you can work with this architecture also with real floating values that's not binary coded?
Mm-hmm. Yes.
Experience?
Yes. So we used one-hot encoding just for the example purpose, just to make things simple, so that we don't really have to train the embeddings first and then use them. But yeah, I have used word embeddings in other applications using LSTMs, and it works just fine with the float values as well. And it doesn't really have to be even positive or negative. It doesn't really care as long as the values are either normalized or corresponding to that. Yeah. Yes. Yes. Right. So you're right that we can use the variable length. We can keep, like, for example, we have some sentences with length 10, 11, and 12. We can keep the length same and still use the training model that we have. But for that, you have to make sure that all the sentences in a particular batch are of same size. So in that case, you have to collect all the tweets, all the sentences of the same length, and pass them together, because that's how we define the model, define the placeholder that it's going to have some maximum length, and we have to define that so that all the values in that matrix, final 3D matrix, are same. So basically to make the dimension consistent across one batch.
One more question. You were working with a predefined dictionary. Let's say 200 words, 40,000 words. Is there any strategy to work with a training dictionary that has, for example, 40,000 words, and after that you get examples from real world with new words that are not inside of the dictionary?
Right.
How do you work with that?
Right. So again, this example was a simpler one, and that's why we use one-hot encoding. And if you use one-hot encoding, there may be some words that are not in your dictionary, and for that you don't really have an index, so you can't really make one-hot encoding. That's right. So first of all, in production environments, we always use word embeddings. So we can always have some sort of embedding for a new word that we see that's default, and all these embeddings are also going to be tunable while we train. So even if we come up with some word embeddings based on the context on a particular dictionary, and we get some new word, we can assign some default word embedding to that, and then pass that along with the other words, and it's going to be tunable accordingly in that context. So it's going to take the values according to the words that it's coming next to. So we can still go with that even if we see some new word. Yeah.
One question about the word embedding. My problem was that I couldn't get the implementation to work on GPU, and everything in TensorFlow in the embedding forces the operation on the CPU. Have you managed to get embedding working on the GPU?
You mean you have some data, and on the basis of that, you are trying to create embeddings for your data, right?
I created some network that also uses the embedding.
Yeah.
And I tried to train it, which worked, but it was really, really slow. And then I looked at the TensorFlow graph, and it just didn't want to move the embedding part, this lookup part, to the GPU. And then I looked some more, and it was said that there's some new function that does it. So I wondered if you managed ever to get an embedding working on the GPU.
Yeah, actually, the application that I was working on, we are training on GPU only, so I didn't really have any problem like that, but we can see if, we can talk about that later if there is some specific case about that particular one, yeah.
And it always moved all operations to CPU and was really, really slow.
Okay, that's weird because I actually used GPU quite a lot on Google platform to actually train the LSTM, so it worked just fine. Yeah. Yep, so that's it. Thank you.